Alright guys, this is a sample problem looking at specifically the impulse momentum theorem. So before we begin, the impulse momentum theorem, right here, of course, the left side, force times time is impulse, units of Newton seconds. The right side is the change, specifically the change in momentum. And I wanted to address that part right there, similar to the work kinetic energy theorem from last chapter. This guy is a little bit of a transformer, it can expand itself out. Specifically, right over here. Since this is the change in momentum, of course, this is going to be momentum final minus momentum initial, okay? As well as each of these individually is going to be mass times velocity final minus mass times velocity initial. Final and initial on velocity have subscripts due to the fact that these are going to change, and mass does not, because almost always it doesn't change. So that's why it doesn't have a subscript. Since it doesn't, since this is the same mathematically, we could also factor it out. So this right side can really become any of these guys right here. When doing problems, always write this first to show the impulse momentum theorem, but if you need to transfer to any of these, depending on which one's easiest for your situation, please feel free to do so. Speaking of, here's the problem that you're going to do. What we have here is a football player named what you decide to name them. I don't know. Anyway, and they're a linebacker. Fullback. Big guy, 150 kilograms, is on par with 330 pounds. They are traveling to the left at 4 meters per second. Okay. Upon hitting, say, the front line, somebody there to pop them. They put a force on them, a net force. I think that is very easy to see. So let's just go ahead and make that bigger. Okay. Of 200 newtons for a total of 1.7 seconds. Again, I don't know how easy that is to see. A comment on this. Number one, you'll notice that I only drew one force, and that's because I've told you what the force net is, the force total. This is, in fact, the force diagram that you should draw if you're talking about a force net. The usual force diagrams that we draw have all of the individual forces and would probably look something like this. Gravity would be down on them. Force normal would be up on them. This marker is not very good. And this would be force of, I don't know, linemen on fullback, okay, as they go straight through the line, something like that. But this is what you're used to. But this is all we need if given the net force. The question in play is, after this impulse, after this force, what is the final velocity? I would suggest you try this entirely on your own. I think that it's really not that hard. You'll see that in just a second. One small piece of advice, don't forget, momentum is a vector. So the first thing you're going to want to do is set which direction you want to be positive. I've asked both classes this recently, and it was about 50-50. So it's entirely up to you. I'll do that in just a second. So pause, try to do the problem, and then I'll go over it. And now I'm going to go over it because you totally paused. I appreciate that. So what I decided to do, and again, it's whichever one you want, I decided to make this way positive. You begin, of course, with the impulse momentum theorem. It's going to be hard to see, isn't it? Let's go to red. Let's try that again. There we are. And out of these, I think this, based on what I'm trying to find, is definitely my best option. So this is the impulse times time equals mass times velocity final minus mass times velocity initial. So basic algebra, trying to get that little guy by itself. So let's add that on both sides. And right here, you certainly don't have to know this. As complicated as this looks, this guy right here says momentum initial plus this guy is the change in momentum. Notice it's equal to that, is equal to momentum final. So take however much is in the beginning, add the change, and that gets you the final. But at this point, to find velocity final, we're simply going to divide by m. I gotta hurry. You guys are coming. So this should be 150 kilograms times, I said left is positive, so that would be positive 4 meters per second, plus since the left is positive, net force should be negative 200 newtons times 1.7 seconds all over 150 kilograms, and the answer should be positive 1.73 meters per second, meaning they were traveling left at 4, and this impulse has caused them to stop. Now, let's say for a second that whoever this guy is, that their little brother took their place. Okay? Everything else remaining exactly the same. The only thing that changes here is that instead of 150 kilograms, they are now 25 kilograms. So about a 50, 60 pound kid, third grader, is getting hit by the same adult athlete. What you'll notice here in this problem is that none of this actually changes. Their initial momentum would be about 1/6 of what it previously was, because they have 1/6 of the inertia. Okay? The change, the impulse, would be exactly the same. The amount that it has changed is not any different, because the force is still the same, as is the amount of time. But also the inertia being down here would result in less in that particular case. So we're going to just calculate this again. We have 100 minus 340 divided by 25. We actually end in this case as like negative 9 point, oh shoot, I'm trying to remember. I think it was 4. That's probably off, but several of you are outside right now. I don't want to keep you guys waiting. So there you go. There's a simple problem. And we'll talk about momentum diagrams here either in another video or later today.